对对，
这个
对，重新 share， 重新 share， 来
share，
对，停止，再一次，这边再按一次，然后你用那个全幕，不要用那个没办法看播放 ，OK， 点它，行，然后这个简报，最后这个，好，播放，就我们就可以看到
OK，
好，对，有了。
Sorry for delay. Okay, shall we start? Okay. Okay, good morning. What I'm going to present is the topic. Can you hear me? No sound? What I'm going to present is the topic about innovation of genoscience technology. The word genoscience is a new term for not only you, but also me. It's a new term in Taiwan. Okay, let's go. This is my outline today. Before we start the presentation for detail, I will introduce the STUST. There are some students from Philippines have graduated from STUST, so maybe they can understand what I say. There are 4 colleges in STUST, but we are going to have the 5th college about the College of livelihood, and the Department of Nursing is going to be established. So we are new faculty join, and right now we have more than 500 faculty in STUST and more than 14,000 students, and we have more than 200 sister university. This is the pictures about the STUST. It's the front door, front gate of TUST. And this is campus inside STUST. And this is very beautiful night view in STUST. STUST is in Tainan, Taiwan. This location you can understand from this map. And we have it's a very old city. Tainan is a very old city, more than 2,000 temples. And this one you can see. This is the CEO of NVIDIA, very famous guy. NVIDIA is the biggest AI company, right? And the CEO, Jason Huang, he is a Taiwanese American. And the other AI important person is Lisa Su, is a CEO of AMD company. So these 2 important AI guys are born in Taiwan and Tainan. So you can see the pictures. STUST is one of the partner of NVIDIA on the background of Jason Huang. Okay. Okay, let's talk about BMEC. The history of BMEC's STUST. We start to recruit the master students for the biomedical electronics in 2002. And the Department of Electrical Engineering of STUSC start to recruit undergraduate students for the group of biomedical electronics in 2003. And finally, we established the Biomedical Electronics Center, so-called BMEC, in 2003. So we start the biomedical engineering research in 2002. And there are only a few professors are the founder of the BMEC. And we have at the moment is STUST is very near to Chime Hospital and the Chenggong Hospital. Only 10 or 20 minutes if you drive a car, okay? Now, our professors all come from all have the background of the EE engineering and the computer science. So your faculty, I think, are the same. So traditional application of college EE and the computer science, most of the technologies are applied in the fields of the industry or engineering science for mass production. That's traditionally application. And right now, new applications will be the new trend of EE and the computer science. We want to expand the new application to the field of medical science. For example, biomedical engineering, neuroscience technology, and assistive technology. New applications will need the cross-disciplinary teamwork. Teamwork is very important, I think. That's our best experience during the past 20 years. We have some examples for traditionally and new application comparison. We develop the industry robot for the industry, right? And right now we can use the same technology to find out the new application. We can develop the robot, but for human, not for industry, like the DaVinci medical robot. Okay. Traditional application, we develop the new car or electronic car, okay. And for that general people. But now we can transfer the same technology to develop the scooter or electrical stand-up wheelchair for the disabled. So it's different. We change the applications direction. This is on the left side. This is audio equipment like earphone, speaker. We developed this device for traditional application. But right now, we can use the same techniques to develop a new hearing aids, assistive device. And the traditional application, we must measure the physical sign, like ECG monitor, blood pressure monitor, pulse oximeter to measure our body signal. But right now, we have a Apple Watch to integrate the three functions together, okay? Image processing and the recognition techniques are used for maybe safety surveillance. But right now, we can use the same technique, but apply on the human. Like you can use the same image processing technique to recognize your eye movement, your movement image, and your brain image. MRI like MRI and CT and X-ray. So you have seen the examples I just showed you. Then we want to ask, what is biomedical engineering? So that's very important to understand the definition of biomedical engineering. Then you know why you want to do, okay? Biomedical engineering or medical engineering is the application of engineering principles and the design concept to medicine and biology for healthcare purpose. The field seeks to close the gap between engineering and the medicine, or you can say between engineer and the doctors, physicians, right? Or medical staff, okay? The range of BME, biomedical engineering, is broader than what I say, geoscience technology or assistive technology. The criteria is higher. For example, the level of FDA regulation is very tough, okay? So your product must meet the requirement of FDA, and then you need to spend a lot of money. So it's a very big challenge for BME. Okay, if the criteria is very high to develop the device for medical application, then we can choose some field inside BME, but easier, like geoscience technology and assistive technology. Geoscience technology focus on age and he has a bigger marketing. Okay, he will only focus on age, but assistive technology is a term of for assistive, adaptive, and reactive device. And assistive technology focus on disability. Okay, so that's the difference between the geoscience technology and the assistive technology. Our professors focus on these two fields, and you can see the product example later. Okay, I want to show you two very important example and famous. This one is Intel group, research group. They developed the ACAT for the famous scientist Stephen Hawking. He is an Englishman, and he was severely disabled. He can communicate only with the help his eye movement. He can do nothing but eye movement. So how can the Intel group use the ability he only have, eye movement, to integrate the technology to have a good product to communicate as a tool to communicate with the other people. We call this device, this system, Assistive Context Aware Toolkit, ACAT. It's an open source platform. You can find it on the website, okay? Here is a video for you, but I cannot show the
medicine has not been able
video.
to cure
You
me,
just pray
so I rely
piece by
on
piece,
technology
okay?
to help me communicate and live. I was lucky to lose my voice at the beginning of the personal computing age. Intel has been supporting me for over 25 years, allowing me to do what I love every day.
Everybody can watch his eyes.
Over these years, the world and technology's impact on it has changed dramatically. Technology has changed the way we all live our lives, from communication to genetic research,
Okay,
access to
because of time
information,
limit,
and much
I show
more.
you
As
just hold on,
technology
okay?
has got smarter,
I will terminate, okay? So next example, it's a famous example too. You can see this paralyzed woman can control a robot
two people with
with
tetraplegia.
the help
And there's two
of
people
his
who are unable
brain
to
wave.
move their arms or their legs in any functionally
Her
useful
brain
way.
wave,
We're
okay?
able to control a prosthetic or a robotic arm simply by thinking about the movement of their own paralyzed hand. And they did that using the investigational brain-gate neural interface system. So they thought about using their own arm and hand as though they were reaching out themselves with their own limb, and the robotic arm moved much the way their own arm would have moved. One of the long-standing questions, not only in neuroscience, but in neurorehabilitation, is whether the cells in the motor cortex and other parts of the brain, whether they continue to function the same way years after that original injury.
It is possible for people to use their thoughts
to control devices, either a computer or a robotic arm. The way that happens is that we implant a tiny sensor, just about the size of a baby aspirin, just into the surface of the brain, and that sensor pick up the electrical impulses from a bunch of neurons. And each of those little neurons are like radio broadcast towers, putting out impulses. And when they get to the outside, a computer translator converts the pattern of pulses into something that is a command. One of our participants,
because time limit,
that
we cannot show you
when
so
all of us saw it for the first time.
clearly. Okay. Why I'm going to show you the topic genoscience, because the world's older population grows, and not only for one country, it's very popular in the world. Every country has the same problem. But in Taiwan, we have not only the older population growth problem, we have the other problem, lower birth rate. So this two kind of pressure is very difficult to solve, right? This diagram will show you the pressure of the young guy. They will have this kind of pressure very, very seriously. Okay. Okay. Because time is over, so I must go first. The global trend of geoscience, because geoscience market is bigger than assisted market, because everyone will grow old, but not everyone will be disabled. Okay, so the marketing of geoscience will be bigger than assisted marketing. And finally, I show you two examples for the products developed by STUST. One is BCI control. Okay, this example is show you the similar BCI research as the video you just see, developed by USA, but we don't have so much money, so we our BCI technology adopt invasive measurement, non-invasive measurement, and the USA they adopt the invasive technology. And then the other one,
the Intelligent Rippling Assistive Walker, IRAW, will be introduced as follows. Ladies and gentlemen, it's our great pleasure to introduce the front frame is detachable as well. Special buckle design makes the front frame more convenient for disassembly and assembly, as well as portability. The height of IRAW is adjustable. In order to adjust suitable height for various patients, we adopted 4 linear actuators as the height adjusters. For further analysis, The AR user interface is regarded as the interactive communication channel between the patient and IRAW. Pull the lever to brake. Step on the pedal to park the front wheel. Hope training of the patient with stroke.
Okay, that's two examples developed by STUST. Okay, final, I want to share with you the sentence, change our vision, and we will change our future. If we can amplify our vision, then we can see another beautiful world. Thank you for your attention. Sorry to delay the presentation, okay? Thank you. Because of time limit, so we skip the Q&A, and the final we have we will have a discussion. Okay. 你直接吗？他会讲，他会介绍，你过来吧。第二个是你的在里面哦。
All right, thank you very much once again. Just give me a moment. Once again, ladies and gentlemen, that was Dr. Shi Chong Shen, the convener of Biomedical Electronics Group of STUST, who was able to talk about innovation of geoscience technology. Allow me to reciprocate it once more. We will have our Q&A later on at the end of our webinar. We are now going to proceed to the next part of our webinar, and that is our second speaker. Allow me to introduce to you our second speaker, ladies and gentlemen. All right, our second speaker is Dr. Yu John Chen, who is a professor with a PhD from the Department of Computer Science and Information Engineering at the National Cheng Kung University. His research expertise spans speech communication, assistive technology, biomedical signal processing, natural language and speech processing, and artificial intelligence. With a strong foundation in computational and biomedical sciences, Dr. Chen teaches courses in programming languages, biomedical signal processing, and pattern recognition. His work focuses on advancing AI-driven technologies and assistive communication tools to improve healthcare and human-computer interaction. Ladies and gentlemen, to talk about the application of artificial intelligence in assistive technology, let's give a very resounding virtual applause to the chairman of Department of Electrical Engineering of the Southern Taiwan University of Science and Technology, Dr. Yu John Chen. Good morning, Doc.
Good morning. Okay, good morning. This is my topic, the applications of AI in assistive technology. It's okay. So, in my interesting research topic is focused on AI. So, this talk, I just show some technologies of AI. And I always co-work with Professor Chen. He is also work in the assistive technologies. So I not only for AI because LLM is also very important because I always focus on speech and language signal processing is very important for AI. And sometimes for biomedical engineering, the data is limited, so the deep learning or AI cannot work well in this topic. Therefore, some machine learning technologies should be used in this topic. And so, for the AI or the intelligent systems, it always be a classification task. Just two approaches, statistical approaches or neural network. And recently, most research just focus on neural network. But bioengineering is sometimes cannot work well because of the data size is limited. So the classification can classified into two topics. One is statistical approach, another is neural network approach. For the statistical approach, the data just large data, and the input should be features. So the researchers should be an expert in this research topic, and the model is learning by using statistical technologies. For the neural network, the data should be big. It's much larger than the statistical approaches. And the input, it can be features or just input the raw data. And the feature can be learned by the neural network. So it's learning just from data. It's very easy for some researchers. There can be everyone to work or to reach a research without another knowledge. So for my research, I just focus on brain-computer interface. And in my research, I focus on the algorithm because I'm a computer science. So in this brain-computer interface, we can get the EEG signal or EOG signal and so on. And then we just using the signal processing to find the corresponding response. So input in the EEG signal. And we focus on digital signal processing to remove some noise. And we focus on classification algorithms. Then we can corresponding find the commands. Then this this system can be used for another assistive device. And for brain-computer interface, I always focus on steady-state visual evoked potential signals because the SNR is good than other EEG signals. So first, I introduce AI application. It just use the denoising technology. When the EEG signal obtained from the OZ channels, it always contain many noises. So I use a denoise algorithm. It's just a neural network. It's a denoise autoencoder. Traditional autoencoder without the denoise, it just input should be the same as the output. So it's called the autoencoder. However, for the denoise autoencoder, the output, we assume it to be a sine wave because the EEG signal is invoked by the visual. It will contain one specific frequency. So we assume it to be a sine signal. Then this autoencoder will be a denoise autoencoder. And when the here hidden representation, it just denoted as embedding features. It can be a feature learned from the data and is an unsupervised algorithm. Therefore, according to this algorithm, we can find using another classifier to get the results and the performance just this in this here. And we can find later the DNN and the denoise autoencoder is very good for this application. Next, I using the multitask learning is another neural network technology. It's just to development by the in the training. First, in this topic, it's just one task, and we input one input and one output. But in this multitask, we have two tasks. One is denoise task, and another is classifier task. And this is because we always find that this system just is suitable for your task, but when you change it to another task, it is not good enough. Therefore, multitask can reach good performance. So the performance shown in this here, we can find that multitask learning is also very good. But not only the brain-computer interface using the AI, we also using the EKG to estimate the blood pressure estimation. So just like this. And we can find that we have two input and one output. So these two input, we just input the same signal, but it represents the signal into two different domains. One is time domain and another frequency domain, and we concatenate these embedding features. Then we can find one output. In this neural network, we using the attention layer here. It can weight some key features in the embedding feature. So it's very important for in this neural network structure. So, and the output is shown like in here. And we using the convolution CNN LSTM attention network, and we integration this neural network. We can find this approach can achieve the best performance. And here we also focus on EKG signal, but here we just found CVD decision systems is complex neural network. Here is just very deep, and so it need big data. And in my research group, it's very difficult to collect this data. So I always using open source or open database in the world, and we can compete it with other research group. In this neural network, we using the CSP net and the close attention based transformer. CSP net just like this. In this network, the major important is here, ResNet. Recently, many database, many neural network, we always using the ResNet unit. So this is many more stable for neural network. It's just like this, and it has a ResNet and using the add operation to modify the embedding feature. This is the key point for this neural network, and we can find that it's a deep neural network. And here we also using the transformer. The traditional transformer just one input and one output, sequence by sequence. But in our topic, we just using the close attention network. It's just a multi-head attention. It can using different information at the different layers and to achieve the best performance. So we can find that this performance can achieve the best performance. And recently, I also focus on audio-visual speech recognition, just speech input, lip input, and we concatenate them together, and then rest attention network, just like this one. But we using here is the rest attention network. We can find that it's very similar like this one. This is a ResNet, but we not only using the ResNet, we also focus on channel attention and the spectral attention to find different importance for embedding features and to find the performance. We can find that our performance is also similar to another one, but our model is very small. Okay, this is my research, and thank you very much. Okay.
All right, there you have it, ladies and gentlemen. You have just heard our second topic, and that is the application of artificial intelligence in assistive technology, brought to you by Dr. Yu Ton Chen, the chair of the Department of Electrical Engineering of STUST. This time around, ladies and gentlemen, we are going to proceed now to the next speaker that we have this morning that will be talking about the application of health internet of things in medical electronics system. Once again, our third speaker will be talking about the application of health internet of things in medical electronics system. Allow me to introduce or to formally introduce to you our third speaker. Our third speaker is an associate professor in the Department of Biomedical Engineering at the National University of Chengkung. His research focuses on medical instrument design, electronic circuit, optoelectronic system development, and microcontroller circuit designing. Through his work, he aims to achieve healthcare technologies by integrating engineering principles with biomedical applications. Dr. Wong teaches courses such as biomedical signal measurement, practice, electronics laboratory, electronic systems, drawing and layout for circuit and soldering for electronic components and biomedical devices, and independent study. And at the same time, his contribution to the medical research include the development of innovative medical monitoring system. Notably, his study on a cut-off Les Paul's time-based long-term dynamic blood pressure monitoring system, at which was published in the high-impact Q1 journal. With his expertise in biomedical engineering and electronic system, Dr. Wang continues to drive advancement in medical technology and healthcare solutions. Ladies and gentlemen, to talk about the application of health internet of things in medical electronic system, ladies and gentlemen, let's give a very resounding applause to our third speaker, Dr. Ji Jer Wang. Sir, good morning to you, Doc.
Okay, sorry for that. Because Dr. Huang had some important business, he cannot attend today. So he record a video here to share us. So now I play his video.
My name is Jijer Huang. My research interests are in electrical impedance imaging, the development of bioelectrical impedance analysis technology, the development of non-invasive biomedical measurement technologies, and the design of MCU DSP-based biomedical instrument circuits. Now I focus on the development of behavioral analysis and interactive response measurement for activity ability in elderly people. This is my email address and office. This slide presents the topic of my report, which is the application of Health Internet of Things medical electronics system. The explanation is based on the block diagram below, which is divided into two main parts: the sensing end and the integrated information core. At the sensing end, a microcontroller or DSP chip serves as the controller to receive signals from the sensors. After processing, the controller transmits the data via wireless communication interfaces such as Bluetooth or Wi-Fi to the back end of the integrated information core. The sensing end is powered by micro USB or a lithium battery and can also control indicator lights to display circuit information. The integrated information core can be composed of a computer or structured as a cloud-based system, as shown in the diagram below. These are the topics I want to share today. First, I will discuss the wearable system for monitoring breathing and walking, which comprises textile-based capacitive sensors. The second focus is the interactive system of smart bricks with detection and recognition functions for TUI. Other topics include using air cushion pressure sensors to develop the monitoring infant respiratory system, combined with the novel active safety device, smart toilet physiological signals measurement system, development of a long-term dynamic blood pressure monitoring system using a cuffless method and pulse transit time, a non-perception long-term heart rate monitoring system using non-contact active electrodes. This slide mainly introduces how we use textiles as capacitive sensors to detect people's breathing and gait information. On the left, there is a diagram of the sensor placement, including chest and abdomen electrodes, as well as insole electrodes. The block diagram of the display system is shown on the right, featuring the capacitance detection circuit, which sends the signal to the microcontroller and then transmits it to the smart device via the Bluetooth interface for display, storage, and subsequent analysis. The developed system consists of two electrode structures. The first structure contains the chest and abdominal electrodes embedded in smart clothing, as shown in the figure. The smart clothing is lined with electrodes that make contact with the human skin. The two electrodes on the outside of the chest and abdomen are stitched together with the smart clothing, forming area A. The smart clothing is made of dielectric material with thickness D. The second electrode structure consists of electrodes in the shoe insoles. Each insole contains a reference electrode at the top and 4 electrodes at the bottom. The middle part of the insole is made of latex dielectric material with thickness D', as shown. The capacitance C stat of each electrode structure is calculated using this equation. Our controllers were placed on 3 positions of a subject: the left foot, right foot, and smart clothing, as shown in the figure. It includes photographs of the subject wearing the controllers. Our systems synchronously captured data from the 3 controllers through Bluetooth. The captured real-time and synchronized data included capacitance variations at the toes and heels of the subject, chest and abdomen respiratory signals. The subject walked at different speeds on a treadmill, and our system simultaneously recorded the gait, chest, abdomen, and respiratory waveform signals. For test 1 subject, when the subject recruited in this study walked at different speeds, the waveforms of the toes and heels of the left and right feet were recorded in real time. Simultaneously, the chest and abdominal respiration waveforms were captured. For test 2 subjects, the data is shown here. The waveforms of these 2 subjects are roughly similar. This is also a video of the actual measurement process. We can see that this is the waveform of the toe and heel of the left foot, and this is the toe and heel of the right foot. This is a signal for abdominal breathing.
video。他自己，我原来昨天播就有了，他是在基本上播起的。
Measurements were performed using our system and the commercial device T3s produced by Knox Medical. This device utilizes respiratory inductance plethysmography, RIP, for respiratory measurements. Subjects wore our developed electrodes and the RIP chest-abdomen belts of the T3's device, as shown in the figure. We can see the subject wearing smart clothing and a chest-abdomen belt. The waveform showed when the subject engaged in regular and slow deep breathing. We can measure the subject's abdominal and chest respiratory waveforms in the slide using the Knox T3 RIP and our system. These slides demonstrate that using our system can achieve the same effect as commercial products. This is a video of the actual measurement process. This slide shows that our development system is a non-imaging 3D smart building block system with detection and recognition capabilities. It allows stacking multiple layers of bricks, with each brick requiring no power. Unlike commercially available systems with RFID chips, which cannot perform 3D construction or require imaging systems that are inconvenient to set up and have blind spots, this system provides valuable applications when constructed with building blocks or other devices. This slide shows the differences between using a screen-only GUI interface and the TUI interface we use, which can be compared in terms of interaction mode, sensory stimulation, ease of use, and scope of application. The figure below shows the difference between the two interfaces. We developed smart bricks for TUI. It comprises three main components: bricks, a brick placement base, and a personal computer or smart device. The bricks were designed in various shapes depending on the game content, and a small printed circuit board, PCB, was built into the bricks to enable encoding functionality. The brick placement base features 3x3 circular grooves as the placement areas for the bricks. At the bottom of the base is a brick detection circuit PCB that transmits the detected brick information to the back-end integrated circuit. The information received is then transmitted to a personal computer or smart device via Bluetooth. Consequently, our system can be an interactive game platform for users to display and operate 3D virtual bricks. Currently, 2 interactive serious games are being developed and tested on the elderly using memory games. One is a memory game, and the other is a matching game. Our system not only provides an interactive platform, but also offers users quantitative indicators of time parameters during the operation by the subject. These quantitative indicators can be used for subsequent analysis. This slide shows the detailed process of our game experiment process. It includes instructions, games, and post-game evaluations. This slide shows the conditions for accepting the subjects and the conditions for not accepting the subjects. The following shows the evaluation parameters of the test subject's user experience, SUSCA. This slide displays the overall framework of the developed blood pressure monitoring system. The first section shows a customized office armchair equipped with pairs of electrodes placed on the chair's armrests and legs, a photo detection module composed of an infrared light emitting diode, IR, LED, and a photo detector, seat-mounted gas bags, a micro switch. Block 2 comprises 4 analog circuit subblocks to acquire the necessary physiological signals. Subblock A captures the ECG signal, which is fed to a high common mode rejection ratio instrumentation amplifier. Subblock B captures the PPG waveform with the signal sent to the MCU. Subblock C captures BCG signals. Subblock D contains a strain gauge-based circuit that acts as a micro switch. Block 3 is an MCU module implemented on a microchip. Block 4 is a graphical user interface installed on the PC. The blood pressure monitor was synchronized with the measurement apparatus for an accurate comparison. A 5-minute rest followed the 3-minute measurement, and the experimental protocol concluded with a star 1-minute standard cuff blood pressure test. The experimental protocol is illustrated in the figure below. Figures A, and B illustrate ECG and PPG signals, respectively. Figures C and D illustrate raw BCG signals, which are transformed into BCG and BCG DC signals, respectively, after being filtered by the 2 filter paths. The plot on the left-hand side of figure 5 represents the control signals produced during the deactivation of the discourage valve and activation of the pump, whereas the plot on the right-hand side represents the control signals produced during the deactivation of the pump and activation of the discouraged valve. A differential operation was performed on the ECG, and the R-wave peaks were located using a zero-crossing method. The peaks in both BCG waveforms were located in a similar manner. A differential operation was also performed on the PPG waveform, and the point of the maximum slope was located through peak detection. The second PPG peak was detected using a zero-crossing detector. As illustrated in the figure, RI, P, PAT, and TDB were defined as the time intervals between consecutive peaks in the ECG R wave, the interval between the R wave peak and the point of the maximum PPG slope, the interval between the point of the PPG maximum slope and the second wave peak, respectively. This table compares the regression analyses. The three variable cases yielded comparable performances in terms of R fried, and adjusted R strides for either SBP or DBP estimations, providing evidence that either RJIR or RJIL can replace TDB when TDB is unavailable due to the difficulty in capturing the second PPG peak. Scatter plot of measured versus estimated blood pressures for A, SBP, and B, DBP, along with a linear regression line using PAT, RRI, TDB, and RJIR as the independent variables. A front track non-contact ECG monitoring and analysis system was developed using a capacitive coupled device integrated into a home sofa. Electrodes were placed on the backrest of the sofa, separated from the body by only the chair covering and the user's clothing. The study also incorporates measurements using different fabric materials, and pure cotton was chosen to cover the chair's backrest. The figure displays the measured ECG from 4 different scenarios. It can be observed that when the person is sleeping or reading, both the current system and the commercial device can clearly measure the heart rate. In the event of tea drinking, due to arm movement and a noticeable amount of motion, artifacts distort the signal. The products of the healthcare industry are unconsciously integrated into our living environment. The growing interest in health monitoring during daily life has led many researchers to explore non-conscious biological signal measurements. In this slide, we propose smart toilet equipment that can measure several physiological parameters, including ECG, body weight, and body fat ratio, while also providing health management functions. In the current research, the system's hardware architecture is composed mainly of 3 parts, as shown in the figure. The first part is the instrumentation block. Its basic function is to measure the weight and bioelectrical impedance of the person. And it also measures the electrocardiogram signal processed using a digital filter. The second is the local computer transmission block, which is responsible for transmitting data. Sudden infant death syndrome, SIDS, refers to the sudden death of infants less than 1 year of age. The system is shown in figure 1. The inflation and deflation pumps, pressure sensors, and discouraged valves are interconnected and are controlled via the microcontroller. The alarms, buttons, and indicators constructed in this system are used for sound output, input, and display. Thank you for listening.
All right, there you have it, ladies and gentlemen. You have just heard our third topic, the application of health Internet of Things in medical electronics system, brought to you by the Associate Professor of the Department of Electrical Engineering of the Southern Taiwan University of Science and Technology. Once again, let's give a very resounding applause to Dr. T. Jer Huang. Once again, we would like to inform everybody that right after our 5 speakers, you will have our Q&A session. And also, we encourage everyone as well to relay your questions later on, so that we will be able to capture more fresh ideas and new learnings from our internationally based professors. This time around, ladies and gentlemen, we are going to proceed now to our fourth speaker. And allow me to formally introduce our fourth speaker. Our fourth speaker will be talking about a new era of medical image analysis and serious games in healthcare applications. He is an associate professor with a PhD in biomedical engineering from the National Cheng Kung University. His research expertise lies in image processing and biomedical image analysis, contributing to advancement in medical imaging technologies. Dr. Chen teaches courses in physics, digital image processing and application, and C languages, equipping students with fundamental and advanced computational skills for biomedical applications. His published works include studies in 3D CT scan image processing modeling for orbital, structural measurement, and MRI based research on a- amygdala activation in patients with major depressions undergoing antidepressant treatment. Through his research and teaching, Dr. Chan continues to drive innovation in biomedical image processing and analysis. Ladies and gentlemen, to talk about a new era of medical image analysis and serious games in healthcare applications, let's give a very resounding applause to the Associate Professor of the Department of Electrical Engineering, the Southern Taiwan University of Science and Technology, Dr. Yen Teng Chen. Good morning, Doctor.
OK，哎，我刚不是学了。对对对，OK。OK，大家慢。Okay, good morning, everyone. I'm Yan-Ting Chen. So, because of the time limit, I need to go quickly. So, the topic I would like to share today is my major study about the medical image analysis and the serial scan. And I need to focus on the field of healthcare. And the image processing and analysis, it is a very well-built field and a very long established field in the research. And the major material is X-ray, MRI, and CT scans. And it can help the doctors to diagnose the disease. And based on the information provided from the image analysis, it can have so many information for doctors to extract the features and the patterns from the image data. And it can help the diagnosis. And then the second topic here is develop very quickly the serial scans. And it can use in the not only in the healthcare field, maybe for medicine field. And originally the games designed is only for the entertainment here. And but now it can apply to other field. And the goal to use the games is to encourage the patients can in the therapy activities. So it can can use to in the way of the interactive and enjoyable way to improve the patient to have a well-being. And the first topic here, I would like to introduce the basic techniques of the traditional image processing. And the techniques always need to manually designed by the designer. And they have some basic techniques, include the smoothing, sharpening, and noise filtering, and the image segmentation, edge detection, and the feature extractions. All of the techniques, I will have some examples of our research. Later, I will introduce that. And the features of the image processing, the most characters is all the features should be manually tuned by the designer. And while you change the application, then all of the features should be choose again and to very pay for many attention to tune that. And so the limitation to adaptabilities to the complex image. So in many real applications, the image maybe have some varying lighting condition or have much more of noises. So we need to pay attention how to improve the image qualities based on the image processing techniques. So now the traditional image processing can be focused on the simple, well-constructed images. So if you want to have some more applications by using a traditional image processing, maybe it is very difficult to use. So in my earlier study, I used the image processing techniques for the microscope image tissue classification. So this is real tissues. A microscope, we take it by the microscope, and the image will like that. So we can find out they have the non-uniform illuminations in the images. In the four corners, they get a little dark. So I use the image enhancement to overcome the problem, and use the image segmentation to just classify the nucleus of the cells from the image. Then we just only need to focus on the nucleus variations to classify the cells from the others. And I need to choose some features manually. So we choose some features like that. So all of the features, you can survey the papers to find out how to calculate. And in this application, they have two kinds of applications here. The first one is the feature extraction. We can recognize the different features, different tissues in the image. Some are blood, some are colic, some are follicular cells and fibrous, and maybe space. So based on the different values in the features, we can classify the image, classify them to be the 5 kinds of the features. And the second application here is we can base on the difference, the features difference in the nucleus, and classify the benign tissues from the carcinoma features. So the features below here is evaluated from these features. And all of the features we can calculate for every sub-images, the grid here, every grid of the image. And we can evaluate all of the features and then calculate them, then use the classification rules to classify them. Then this is always based on the image features. I must be emphasized that all of the features should be selected by the user, the designer, and it is very important, depend on his rules, his experience. So now a new kind of the image processing is AI-based and use the deep learning algorithms. And just as the Professor Chen, the second presenter, he said that this kind of algorithms are based on the machine learning and the deep learning. And now the image processing field is a very important application field in for the AI. And the image classification and the feature extraction, maybe we can use the CNN, convolutional neural network. And now they have some other new application based on the vision transformers. And for the image classification and the feature extraction, and another kind of the for the object detection is a YOLO. Maybe some of the friends can already have the experience about it. Then all of the kind of the application, they have open source, and you can search in the internet for the source code, and you can easily to apply that. So just that in this application, you can download the code, source code, and run in your computer. They can detect the person tracking, the movement of the persons in the videos, and it is real time. So the important is not about how to process the image, and so you can focus on the success process to deal with the other works, not only for the image processing techniques. And the features of the AI-based image processing, it can deal with the complex environment and handling the variations in lighting, occlusions, and the perspectives. So you don't need to pay attention how to extract the features, because the algorithm can select features automatically for you. And but the problem is this: it need to learn about the techniques from a large amount of data. That means that although it can eliminate the need for manually feature design, but you need maybe tens of thousands image or even millions of image to let the algorithms to know how to train the features of the image. So it is a training data for the AI system, and it needs more computational power. And so now why the GPU is very necessary for this kind of applications. So because it needs to the computation power, so the system, if it has GPU or even the cloud computing, will be better. So I will skip here. This is just for the algorithms for the AI systems. But now I just emphasize that the CNN is the important application in the image processing. And all of the examples here, the VGG, ResNet, and DenseNet, and maybe YOLO, it will be easy to have the resource from the website. So this is the structure of the CNN. So this is an example that while we can use the X-ray films, then after the features extraction, they have some layers in the CNN. And after that, it can extract the features of the image. Then we think through the classifications layers, then we can classify the COVID-19's images from the normal images. And this is another application. I will skip it here. Now I would like to introduce the features of the image analysis in the healthcare, and the applications can reduce the human errors and misdiagnosis, and provide more information for doctors, and it can lighten the clinical workload, and the doctors can focus on the clinical techniques, and we can support the doctors to making faster and more accurate diagnosis. And now I would like to introduce my second applications for the serial scan. The serial scan, I just focus on the techniques based on image processing. And now it has a very important and a very major application by using MediaPy. And I just emphasize it is open source. You can download that the code from the internet, and it can use for real-time image processing. So it can be used for posture estimation and or hand or face tracking or object detection. And here the best of the MediaPy pose is the CNN. And if you apply that, you can find out the 33 human beings landmarks in the video and tracking the behavior of the person that track. It is very useful for fitness analysis, motion capture, and other AR applications. And this is some of my study. This is for the functional fitness test for older adults, and there's some measures based on the post landmarks, and we can track the behaviors by the skeleton here, and they have some tests. They can evaluate the fitness of the subject, and this one is we call the get speed test, and the second one, okay, let's just one leg stand, and this group AWGS, they have some rules for the test to evaluate the performance of the subject. So we use the subject performance and to evaluate his based on the skeleton to evaluate their performance. Okay. research. Okay, so this is another kind of application of us, and we call that the virtual coach of Tai Chi Kung Fu system. And in this system, we have use the media pi to capture the real Tai Chi coach, and one video from the in front of him, and one from the lateral side, and based on the skeleton's information, we build a virtual coach from his posture. And while the people can wear the smart glasses, and then the virtual coach can display in front of him, and so he can wear the glasses and play the Tai Chi system at home. So just like this. That is from the lateral view. It is from the other side view. So it is a three-dimensional virtual coach, and we have use that in the community activities. Let them play the Tai Chi systems. Okay, I think that because of the time limit, so I just have some introduction here, and I think that because of traditional image processing is all so much limitations. So, but now the AI system can help the image processing field have a new era for the beginning, and I think that it will be very big development in the future. Thank you for your attention. Okay.
All right. All right. There you have it, ladies and gentlemen. You have just heard our fourth topic, which was a new era of medical image analysis and serious games in healthcare applications. Once again, our profound gratitude to our fourth speaker, Dr. Yen Tang Chen, the Associate Professor of the Department of Electrical Engineering of ST, or Southern Taiwan University of Science and Technology. This time around, ladies and gentlemen, once again, I'd like to remind you all that right after our fifth speaker, we will have our open forum, which will be including the question and answer portion. And at the same time, that will be the opportunity for each one as well, for each one of us as well, to be able to capture new perspectives in the context of biomedical engineering, and at the same time, to be clarified on the things that we wanted to be raised. This time, allow me to introduce to you our next presenter, our fourth, our fifth speaker, who will be talking about the application of biosignal processing and analysis in healthcare. Allow me to introduce our fifth speaker. She holds a PhD in biomedical engineering from the National Cheng Kung University and a bachelor's degree in nursing from the China Medical University, with a strong interdisciplinary background in both healthcare and engineering. She has dedicated her career to advancing biomedical technology. Currently, a faculty member in the Department of Electrical Engineering at Southern Taiwan University of Science and Technology. Dr. Hu previously served in the Department of Nursing at Central Taiwan University of Science and Technology and worked at Hospital under the Department of Health Executive 1 ROC. Her research interests include healthcare technology, biomedical signal processing, and assistive devices. Through her work, Dr. Hu contributes to the development of innovative medical technologies aimed to improving patient care and clinical efficiency. Ladies and gentlemen, to talk about the application of biosignal processing and analysis in healthcare, let's give a very resounding applause to our fifth speaker, the Assistant Professor of the Department of Electrical Engineering of the Southern Taiwan University of Science and Technology, Dr. Tun Ju Ho. Good morning, Doc.
Good morning.
不要分享，哎，历史分享，然后你要切你的，哎，对，那个，哎，整个音，然后选你的，然后选播放。
Okay, good morning. This is my topic about biosignal application in healthcare. I have a bachelor degree in nursing and a PhD in biomedical engineering. I passed the National Nursing Certificate exam, and I work in hospital from 1992 to 1994. I have engaged in biomedical engineering, education, research, and service for over 20 years, from 2004 to till date. I combine the knowledge of nursing care and biomedical engineering technology to conduct my research, including biomedical signal processing and analysis, and healthcare technology. Part one, measuring analysis and recognition of lung sound. Auscultation of lung sound, reflecting the situation of the air flow in the respiratory tract. The stethoscope is a non-invasive, convenient, and inexpensive device comparing with X-ray, CT, and MRI. In clinics, doctors still use traditional stethoscope. It denotes a professional symbol for physicians. A problem in healthcare, lack of clinical manpower, care attendant and family caregivers instead of professional nurses. They cannot decide when the sputum can be cleared. According to them et al. Report, the work experience of a doctor is smaller than 2 years or over than 8 years. Their auscultative skills are declining. With the advancement of digital signal processing and artificial intelligence, electronic stethoscopes can combine these technologies to assist doctor in diagnosis. We have to know how to identify normal lung sounds and abnormal lung sounds. Normal lung sounds include bronchial or tracheal sounds, bronchovascular sounds, and vascular sounds. The location of auscultation is shown the left picture. Abnormal lung sounds include continuous sounds, wheeze, bronchi, and stridor, and discontinuous sounds, cross-crackle and fine crackle. The feature of abnormal lung sound include time duration and frequency. For American Thoracic Society, for example, wheeze, time duration is more than 250 milliseconds, and the frequency is more than 500 hertz. We study literatures and summarize the relationship between disease and the lung sounds. For example, bronchitis include appear cross-crackle, wheeze, or sputum sound. Secretion and sputum result in airway obstruction. For endotracheal suction, nurses have to use auscultative skill to listen lung sounds in the period of pre-suctioning and post-suctioning. So our purpose is to develop a computer-aided auscultation system for measuring and analysis of sputum sounds and the e-learning instruction for postural drainage. This picture is postural drainage. and to establish the signal processing, analysis, and the recognition system of lung sounds and breathing patterns for assisting medical staff in respiratory care. The purpose of hardware circuit design of the stethoscope is to train our students' ability of circuit implementation and analysis. We use a stethoscope diaphragm combined with microphone to convert sound waves into electrical signals. And we also design hardware circuit to remove noise and amplify signals. And we also calibrate the circuit to check whether it meets our specifications of the lung sound measurement system. For lung sound, the range of frequency response is 20 Hertz to 1,200 Hertz. In our circuit, the ratio of output to input voltage is linear within the input amplitude of 60 millivolt and 40-degree gains. And we also design software GUI using MATLAB. A breathing cycle includes inspiratory period and expiratory period. So in measuring of the lung sound, the user can click on the location of lung sound, the position, and recall the file, and signal processing and signal analysis. Signal processing remove noise, and we can take in of a breathing cycle. Signal processing include signal detrending, adaptive filtering, notch filtering, bandpass filtering, and signal truncation. Signal analysis includes spectral analysis, time frequency analysis, wavelet analysis. We also recognition model. We use discriminant analysis and backpropagation neural network. Signals analysis. We power spectrum density PSD estimation. We use Welch method and extract 8 parameters. And short-time Fourier transform extract 2 parameters: time, duration, and frequency. Discrete wavelet transform can use to decompose signal into different frequency band, and we remove unwanted frequency band and extract 20 parameters. And then we use statistical stepwise method to select significant parameters to recognize abnormal lung sounds. We compare discriminant analysis, DA, with backpropagation neural network, BNN. The results show the accuracy of BNN is better than DA in recognizing normal lung sound, critical, wheeze, or runtime. And we apply for a patent in Taiwan and encourage our students to participate in domestic and international competitions. We also achieve great results, such as a Gold Prize Award. And we use DSP technique to physical signal analysis. The relationship between physical signal and emotion response. We can see skin resistance. We can use GSR. Body temperature measured by SKT. Heart rate change measured by ECG. Vessel contraction measured by PPG. Muscle contraction measured by EMG. And cerebral cortex electric potential measured by EEG. So we can recognize emotion state such as happy, sad, fear, and disgust. These 4 topics are my student dissertation. Is focused on elder emotion response detection, depression patient, stress state, and so on. Part 2, application of pressure sensing technology. In Taiwan, population of people in need of long-term care is about 860,000. It reported in 2023. Taiwanese elder people spend an average of 8 years in bed before death. Problem of sleep in bed include insomnia, apnea, and bed safety, such as restlessness, falling down from bed, and lying without changing posture, resulting in pressure sore. So we choose pressure sensing technique to solve the problem. We consider the human anatomy and physiology, such as the width of the shoulder, body weight, and the body height, as well as engineering design, such as selection of sensor, distance between sensor, and circuit wiring. We choose force sensing resistor, FSR. We design a 12 by 18 square force sensor FSR pressure matrix that measure the entire the length of the body. Because the one FSR is very expensive, about $300 NT. We redesign our matrix. We reduce pressure sensor to 49 and making a 7 by 7 array, and place the pressure pad between the back or body and the general matrix. We want to know the bed riding behavior. So behavior is like is such as movement, posture, position out of bed. So we analyze, we estimate activity score of pressure signal to identify change of posture, restlessness, and or quiet, and estimate vertical and horizontal projection of pressure signal to identify posture, and estimate some of the projection of pressure signal to identify out of bed. This picture is the posture recognition. 5 posture: supine, left lying, right lying, right edge, and left edge. The red color is high. The high is mean the high pressure. And we also can see the shape of the body. The posture recognition, the accuracy is 94.3%. In out of bed and the posture change, the accuracy is 100%. In movement recognition, restlessness, the accuracy is 70%. The signal fusion method can be used to estimate the breathing rate and sleep apnea. We use the sensor in 4th row to 4th row, major chest movement, and 5th row to 7th row, major abdomen movement. the upper right picture, this is chest movement. This is abdomen movement. The lower picture is measured by PSG device. It's a commercial device. So the signal, the flat part of the signal denote obstructive apnea. The signal of two device, our pressure sensing matrix and PSG device are similar. So we conclude that our pressure sensing matrix can be used for sleep apnea detection at home. We also use the same technique to analyze the foot pressure. So we design pressure sensing insole. So each insole has 12 sensors. We also train students to build the hardware circuit. This is the sensor location and wiring. Parameter extraction from pressure sensor. We include one spatial feature, center of pressure, COP, and 7 temporal features. We can use this feature to recognize gait pattern. Okay. So here we can look here. The red color is the center of pressure. We call body weight. In the working state, the body weight showing to right and left, and blue color and black color is the one leg, left leg, left foot, and right foot. The pressure, the center of pressure. I think this system can be further combined with AIoT and AI to improve healthcare problem. So because the time limit, time constraint, so I briefly introduce my research. I hope can give you some idea. Thanks for your attention.
Ladies and gentlemen, once again, that was our fifth speaker talking about application of biosignal processing and analysis in healthcare, brought to you by Dr. Chun Jung Ho, the assistant professor of the Department of Electrical Engineering at the Southern Taiwan University of Science and Technology. Once again, ma'am and sirs, thank you very much for patiently waiting. This time, we are going to proceed now to the most awaited part of our webinar, and that is going to be our question and answer portion. This time, we invite our dearest delegates and online participants to raise their clarifications or questions. I know that our uh, esteemed speakers are willing, at the same time, very excited to answer those questions as well. So you may send your question in our comment section so that it will be read as well by me and, of course, be heard by our speakers. Okay, any questions po? All right. Once again, thank you very much, doctors from the Southern Taiwan University of Science and Technology. We do have question here. Is the STUST open to collaboration with the Philippine researchers related to biomedical research? This particular question is being raised by Sir Eduardo Ricardo Sajonia Jr. And that question will be
so are we
Yes, sir.
这学生来，有吗？有学生来吗？来这来这边。
大概是有。
By the way, sir, the first question will be, is the STUST open to collaboration with the Philippine researchers related to biomedical research?
哎，他说非他什么？在你跟蒙利安哦。
哦，他是说在这一堂的security的那个。OK， 那我回一下。
哦，这个 IRB 嘛，
So I found that they have he says that how to make sure the patient's data for training and the data privacy and the security. So we have a review board to make sure our experiment is illegal. So all of the patient's data cannot access from other groups. So we have a committee from hospital to review our project and experimental tests. So I don't know, it is similar in the Philippines. In our Taiwan, we have IRB, we call that IRB. 全名是什么？
IRB.
The full name of the IRB. So from the hospital, we need to submit our proposal of project to review our project is illegal, and it will make sure all of the subject is safe during this experiments. So after that, they agree with our project, then we can continue the clinical test. Even for the serious game, it is almost the same. Not only for the clinical image analysis.
Thank you very much for that, Doc. And we do have another question, Doc, from the comment section. And this is also for Dr. Yenteng Chen. It's you again, Doc. And the question, Doc, is, given that the AI in biomedical engineering relies on vast amount of patient data for training models, how can we ensure data privacy and security while using this sensitive information for AI or artificial intelligence or machine learning processes? What are the best practices for regulations in place to protect patient confidentiality?
How long does the commercial process?
Case by case.
Commercial, 我们也有看懂。On the commercial process, typically take for the biomedical.
Commercialized process.
And what are the key stage involved in Taiwan?
对，
什么意思？
So commercial process commercial process for medical instrument usually must pass clinical trial for phase. And we usually need to maybe 5 to 10 years. So it's very long time for medical instrument.
Siya man nag-direct lahat kung ano yung attitude sa direction. Nangyari na, kulang na net-traffic controller sa US.
这边也可以看啊。
Na-assign niya the same, hindi nila the same attitude. Dapat hindi rara kasi may lahat.
Thank you very much for that one, Doc. And Doc, we do have another question here.
有没有？We don't know if any sandwich program 都没有吗？
We have a question here, Professor. This is actually from Engineer Alain Jessel Macas, one of the alumna from your institution as well. How long does the commercialization process typically take for biomedical devices, and what are the key stages involved in Taiwan?
Yeah, I have answered just your question, right? He asked just your question because
Hi, thank you. Thank you very much, Doc, for clarifying. Thank you, Doc. And thank you, Doc. Yeah, thank you, Doc. We do have another question. This is actually raised by Dr. Cindy Liego. The question goes like this: are there any known bad effects on health with having sensor devices or signal processing devices placed very close to the body? The question goes like this: are there any bad effects on health with having sensor devices or signal processing devices placed very close to the body?
Bad effects on health.
是我的吗？我不知道这个是谁。
每个人都有。
No, the effect of the health.
Maybe, but it can be solved.
不是，你来问看，这个是什么意思？
啊？
这个。
来
So,
Bad effects 那个是指说装在身体上面有没有安全性？对，是不是有什么副作用？当你身体用刷机者那一个它绑身体。
Yeah. 哦。
所以你安全性安全性规范就是你们那个还有黄记者那个装在身上的时候会有什么 bad effect？ 那个叫 bad effect，the very low bad effect 啊 ，health sensor device， 就是是不是有装置或者是讯号处理的时候量测的时候会不会更有你的那个声学影响
？Sometimes is the effect of on the health. We choose sensor. We using commercial sensor. Like ECG sensor, we use ECG the pad, and circuit hardware. We will design isolation circuit to protect the patient. So and we also to check our circuit, the security, the safety. So I think we consider this problem. So the place I think is no harm, no problem to the patient. 对吧？第一个吧。啊，你要不要讲一下你的他对病人有没有伤害？
Regarding the problem of bad effects on health, I think according to my experience, even individual has this problem, but the problem can be solved if you discuss with the doctor, and then we can have suitable sensors for the subject. So we think we don't need to worry about the bad effects. If the individual has the problem, we can change the subject or go to doctor and find out the solution. Okay.
Thank you very much for that, Doc. And by the way, we do have another question, Doc, and this is addressed to Dr. Yenteng Chen. And the question goes like this: given that the AI in biomedical engineering relies on vast amounts of patient data for training models, how can we ensure data privacy and security while using the sensitive information for AI or machine learning processing? What are the best practices or regulation placed to protect patient confidentiality?
不一样，这个不一样。最大的，
他说你的。 I think could you show the message about the problem? Which message?
Let me send it again, Doc. Here is the question. This was actually raised by Miss Macorol.
这里，这个，
Make sure the privacy.
and the security.
Is this question?
What the best practice or regulation in place to protect patients? 重新问一次。Okay. So
Institute of Research Board.
IRB. In Taiwan, we have a board in the hospital. They can review the project or research while you do the test for the subject, and they need to make sure the safety of the subjects, and we need to have some rules in the experiment that make sure that the personal data cannot open for another people, even for other researchers or friends or the publics. So we have very rigid rules to protect the safety of the patients. Okay, the IRB, the name is the Institutional Review Board. So if you want to go to the want to have a new test, then need to submit the project, how to do the experiments in the subject in the project to the subject, and tell the IRB to allow you can do that, and finish the experiment. You need to have a report to the IRB, and the important is while you finish your research, while you submit your paper to the journal, they will ask you, do you have the agreement contract from the IRB? So in the process, it is very rigid for us to make sure the safety and the privacy of the patients or subjects. Even the AI model processing, it is again the same, because just as I show you the pictures or videos, even the people that cannot show out, just only capture the video, no any medical treatment or maybe injury. It just only takes the video. It has the privacy problems. So IRB need to make sure all of that is illegal. Okay, that's my answer. And is this okay?
Thank you very much for that one, Doc. By the way, Doc, we do have one last question, and this is actually addressed to any one of you who would love to share something about this question. Allow me to send it once more. The question is coming from one of our innovative student, a young innovator from our university. We have future engineer Luis Nicolas, to which his question is, um, would any one of you would like to share about the haptics research, because it is something that is interested about? Uh, he wanted to ask about your opinion about the haptics research.
Aaron Su.
我看一下，触觉
对，那个触觉的，
是触觉吗？
触觉。
刚刚已经讲了。
触觉，你跟他说一下，就是触觉是那个他们的。
The last question is about haptics research, right?
Yes, sir.
This research is finished by the other professor, Aaron C. But he has left STUST. Actually, he is my PhD student. So if you have if you want to have more information about this research, you can send email or information to RNC or me, okay? Anyone, if you have more questions, you can send your questions to all of the professors in STUST. You can find the email address on our website, okay?
Thank you very much for sharing that one, sir. By the way, we also uh, wrote the name that you have mentioned earlier, and that was Dr. Aaron C. as well. Nothing to worry. I will also be able to make sure that this particular student will be connecting with Aaron C. with regards to the haptics. All right. Thank you very much. Once
So this is the final question, right? And
yes, sir.
thank
That
you.
was the last
Uh,
question.
okay.
So thank you very much as well
Uh,
for
Finally, I
answering
want
our.
to say
Yes, sir.
welcome all of you to visit STUST, or you can send your information or your question to our email to contact with us. If we have cooperation, that's very important. You know, cooperation and teamwork is most important in bioengineering because it's just like I say that it's a close interdisciplinary teamwork, right? So thank you again and welcome to visit STUST.
Thank you very much, Doc, for sharing that one. And we look forward to more collaborations and, of course, opportunities, of course, offered by your institution. This time around, Docs, allow us to give this token of appreciation for allowing us to conduct this webinar with you all. I know that you are all very busy with your undertakings in your institution right now, but then again, you gave us a slice of your time that really allowed us to know more about the general aspects or the overview of the biomedical engineering, and that this particular webinar really pushes us to do more and be more as well in this. So with that, allow us to give this certificate of appreciation and allow me to read the citation. Certificate of appreciation is presented to the following speakers in great